Okay, the next question concerns the energy and the power in a wave. Okay, so we have a wave where we have amplitude of the oscillations being 0.63 meters, frequency 7.75 hertz, and there's more information, but that alone is enough to give you what you need, a lot of what you need to analyze this. So let's analyze that, because if the amplitude is 0.63 meters, if you know the amplitude and the frequency, which here is 7.75 hertz, then you know the simple harmonic motion of a point on the wave. Now, different points on the wave are in simple harmonic motion with different phases, so you have phase changes across the wave, but you have the same simple harmonic motion at every point. It just isn't all synchronous. Okay, so if we can analyze that simple harmonic motion, we can get the energy. The reason because you know the energy of a mass in simple harmonic motion if you know the amplitude and frequency of the motion. Now let's see how that works. Okay, so every point's in simple harmonic motion with an amplitude of 0.63 meters and a frequency of 7.75 hertz. That implies the circular model. Okay, and you should be aware of the circular model. I'm not going to go into great deal of detail, but you have a reference point moving around the circle with some velocity, and the projection of that point on any axis through the center is going to give you simple harmonic motion on that axis. If we project, say, down to the x-axis, then the simple harmonic motion is this way. If we project over to the y-axis, it's this way. The only difference in those motions is phase. They have exactly the same energy. Okay, so we have angular frequency then, which is, well, frequency is the number of times you go around the circle in a second, and the angular frequency is the angle through which you pass in a second. You multiply the number of cycles per second times the 2 pi radians per cycle, and you get 15 pi radians per second. Not sure what happened to my radian there. Okay. Now we have everything we need to analyze the motion of the simple harmonic oscillator. But the thing that we know is that the energy of a mass in simple harmonic motion is always the sum of its kinetic and potential energies. Now, simple harmonic motion, the sum of the kinetic and potential is always the same because the energy of the oscillator never varies. This is an ideal oscillator, of course, with no dissipation of energy. Okay, so the potential energy at some times is 0, which means that the kinetic energy will be at its max. And the max kinetic energy is going to be equal to the total energy of the oscillator. Also, the kinetic energy at some points is 0. The oscillator has to come to rest before it changes direction, so that the potential energy, the maximum potential energy the maximum potential energy is equal to the total energy, the kinetic plus the potential. Well, from that, we then take additional information. And let's back up a second. If we look at this model, the velocity of the point on the reference circle matches the maximum possible velocity, which gives you the maximum kinetic energy. And that will occur if we're projecting onto the x-axis. That will occur when the reference point is down here or up here. Then the kinetic energy will be of any particle will be 1/2 its mass times the square of this velocity. We get this velocity in a very straightforward manner. We multiply the angular frequency by the radius using the fact that a radian of angle times a meter of radius is going to give us a meter of arc distance. So multiplying the radians per second times the radius gives us an arc distance, and we go from radians per second to meters per second. And I'm saying that kind of quickly. That's something you should know from your knowledge of simple harmonic motion. Okay. we conclude that the velocity of this reference point is 32 meters per second, just multiplying the 15 pi over 2 radians per second by the 0.63 meters. And, I forgot to divide by 2. That should really be 16 meters per second. So there's an error there. Let me see if I want to correct that or just go on. When I did the calculation, I estimated 15 pi to be around 46, 47. 0.63 is 2/3. Really, that estimate should have been probably 29 or 30 meters per second, but I forgot to divide by 2. So that should be more like 15 meters per second, a little less than half. And that's going to throw all our energy calculations off, so be aware of that. Okay? And I'll just put a little note here, but then I'm going to go on. Okay, so correcting this, I think that's going to be more like 15 meters per second, and that's going to affect our calculation of energy. It's going to affect us over here. Let's see how we proceed, though. Now, we now look at the problem again. We know that there's some mass density in the string, or whatever the medium is, 2.5 grams per meter in this case. So the mass in a distance delta x is delta m, 2.5 grams per meter, multiplied by delta x. We multiply the number of grams per meter by the number of meters. Maximum kinetic energy of that mass is what? 1/2 the delta m times max velocity squared. The delta m is the 2.5 grams per meter, which is 0.0025 kilograms per meter. Vmax squared, well, I used the 32 meters per second, and I got 1.25 kilogram meter per second squared times delta x. Units of that come out right. When we put in delta x in meters, that would come out kilogram meter squared per second squared, or joules. That would be the maximum kinetic energy of our mass delta m in a small increment delta x. Now I choose a small increment delta x. Why? Because even though the wave is changing in space, a very small increment of the wave will all move together with the same amplitude, the 0.63 meter amplitude, and it will move in simple harmonic motion in this manner. So we assume delta x is small so that none of the particles in the delta x length are significantly out of phase with any of the others. So they're all, again, moving together in simple harmonic motion. Okay. Now, to get this, I used the 32. If I'd used half that much, I'd have gotten 1/4 this, which would be a little over 0.3. If I use 15 meters per second, which is even a little less, that's going to come down to about 0.3 or a little less. So I'm not going to clutter up what we have here. I'm just going to say now the energy would be 0.3 kilogram meters per second squared times delta x. The energy per unit of length would be what? Well, we're going to divide the energy in this length by the length. And when we do, we find that the energy per unit length is 1.2 kilogram. It'll actually come out 1.25 kilogram meters per second squared when we divide by delta x. But I'm going to put a meter squared up here and a meter in the denominator down here to give us joules up here. Meters down here, we have joules per meter. That's a reasonable unit for energy per unit length. So our energy per unit length is about 0.3 joules per meter. Now I had the 1.25 joules per meter based on the incorrect 32 meter per second. So I kind of got an X there in a correction. It should be 0.3 joules per meter, or probably just a little less. Now we're given that this wave has, or that we're talking about a 6 meter segment of this wave. Now we had the 1.25 joules per meter in the wave. That should be 0.3, and I'll probably put a correction up there. We take the energy per meter and we multiply it by the 6 meters, okay? Wave is propagating at 22 meters per second. How much power is required? Well, if we focus on the 6 meter length, it's going to take 6 meters over 22 meters per second, 0.27 seconds for the wave to pass through that 6 meters. So we're going to have to supply 6 meters worth of energy to the wave every 0.27 seconds. Okay? So it's going to take it that long to travel the 6 meters. We need 6 meters times 1.25 joules per meter, or 7.5 joules in that 6 meters. Okay, to establish the wave in that section. So the power required is going to be that energy, 7.5 joules divided by 0.27 seconds, which comes out around 29 joules per second, or 29 watts. Now, I'm going to go through and mark out the 1.25, change it to the 0.3s, and make the according revisions. Okay, straightforward modification. It's 0.3 joules per meter, not 1.25, and 0.3 is an approximation itself. So that when we multiply the 6 meters by the number of joules per meter, we multiply it by the 0.3 joules per meter to get 1.8 joules. And then instead of dividing the 7.5 joules by the 0.25 seconds to get our power, we divide the 1.8 joules by 0.27 seconds, and we get something pretty close to 7 joules per second, or 7 watts. So there's the numerical correction. The reasoning is still the same as before. Now, a more elegant formulation that doesn't rely on the 6 meters or the 22 meters per second is simply that the power is the energy per unit length times the propagation velocity, which is energy per unit length multiplied by the length per unit of time, using length here as the new length that emerges in the wave when the wave propagates through a certain distance. Okay, so it's basically energy per meter times the number of meters over the time, which is energy per unit of time. So that's illegible. I can't even read it, but it's energy over time, and I don't want it to interfere too much with this next situation. And you should think that through. You should understand why that's the case, why we don't have to rely on the specific 6 meter length, why we can just use the energy per unit length and the velocity and shortcut that line of reasoning to get the equivalent result.